So, hello again to everybody. Our next speaker is Vladimiro González-Zelaya. He studied his bachelor and master degree in the National University Autonomous of Mexico. And he is one of my students that decide to work in the academic way. So he did his PhD in Newcastle University, where actually he has a position in this university. And during the time that Vladi was my student, he learns me game theory because he loves these games in general. He's an international player of Go. We organized together the first workshop of Go in our faculty, which is now a classic for every year. And he made a very nice apps to play with mathematics, to learn and to enjoy the mathematics for children. This is very nice. I recommend you to look for this. And he loves the photography too. And so for this and many other reasons, it's for me really a great honor and place to introduce to, as we call, a lovely Bloody. So.
Okay. So, thanks a lot, Rita. It's a pleasure. Thanks for having me at CaRT. And today, let me actually share my screen so I can start with the talk. And yeah, so as you can probably see, CaRT is combinatorics and related topics. And I need to tell you that this is probably be more the RT than the C, right? So it's going to be more the related topics, but I still try to include as much combinatorics as I could, because I think that's probably what's more interesting to most of you. So, okay, so I'm going to be telling you a little bit about AI. And I'm sure we all already know that AI is changing the world. For example, AI can already write much better than probably all of us could, right? Like, for example, this was just like a silly thing I was trying with it. I asked ChatGPT to write a sonnet about the risks of AI, and it came up with this, which is amazing, right? It rhymes, it has structure, it has everything. I'm sure I could never write a sonnet as good as this. Likewise, you can ask it to generate images. And as you can see here, the progress has been like quite notable, right? So from 2022, you can see here the progression of the very same prompt, asking it to generate some image about a photo shoot inspired by Van Gogh. And the progress in every iteration is very impressive. And I was just curious, like, how would it do today? And this is the final image, right? So this is what I got like 1 hour ago. So and I agree. I think this is like probably the best one of the bunch. Even though like the previous one looks more like a photography, this one actually captures the style of Van Gogh, and I feel that's even more impressive than just showing you something like a picture. Other things it can do, it's not only about generating content, but it can actually slowly start replacing like even manual labor. Like Amazon right now, they have these massive robotic arms that they use, and they can like sort the different orders, and they can package, and they can move things around their factories. So it is quite impressive. And because of this and many other reasons, I became when I was starting my PhD, I became really interested in the notion of responsible AI. So by responsible AI, we refer to a set of human notions or human values, which we probably would want any automated system to comply with, right? So. Many of these are like self-explanatory. There's things such as fairness, there is privacy, and some of them are not as clear, right? Like it is not immediately clear what we mean by transparency or accountability, but I'm going to be telling you a little bit about some of this. I'm going to be telling you mostly about fairness because that is my main interest. But I will also talk a little bit about privacy. I will talk a little bit about inclusiveness, and I will talk a little bit about transparency today. So let's begin with transparency. And what do we mean by that? So in AI, we usually run these algorithms. So AI is like one way to call it. Another way to call it is machine learning. And there are many different algorithms in machine learning, and they are amazing. As you have already seen in the examples I gave you, they can generate stuff, they can make predictions, they can do a lot of different things. But the thing is, usually the better a model performs, the harder it is to understand what it is doing, right? So these days, most of the models that are being deployed are based on an architecture called a neural network, but that's by no means the only kind of model that you can deploy. There are other things that are like random forests, decision trees, support vector machines, and whatnot. And the thing is, as I told you, usually the better they are, the harder they are to understand. So this is a very famous trade-off that exists in machine learning that's called the accuracy interpretability trade-off. So usually you would like to have a model that's at the same time really good, but also really easy to understand. And that's usually not the case. Usually you need to give up a little bit of performance in exchange for having a little bit more of intelligibility of the model. So neural networks and most of the fancy models that are used today are what we call a black box model. So the reason we call them black box model is because they do their thing without, as if they were magic, as Rita was saying, right? Like basically you feed it, for example, an image and it will know that this is a butterfly or this is an insect, but it is not immediately obvious why the model knows that this is an insect. And since we want to be able to use these models, even though they are not great at explaining what they did, there is like a recent development, which is to develop a second family of algorithms, which are called explainers. So what an explainer does is to take a model and try to figure out in a human understandable way what the algorithm is doing, and then we can use it to figure out exactly what is going on, right? So, and these are called explainers. The one shown in the white box is a method called the SHAP, which is actually based in game theory, in something called Shapley values. So I recommend you look that up if you can, because it's like really interesting how they work. But I'm not going to go through that today. Okay, so why is it important for us to understand what a model is doing? So, for example, if we were trying to use a model to decide what illness a patient has, right? So let's say we have a list of the symptoms of a patient, right? So they are sneezing, maybe they have some certain weight, they have some headaches, they have certain age. You can tell whether they are fatigued or not. And then based on this, like your typical machine learning model will tell you, okay, this person has the flu, right? But that is not good enough. That is not good enough because it is hard for a patient to just trust a system without knowing like the reasons why they came to this conclusion, right? So that's where an explainer may come in. And for example, here, based on the symptoms, we could get like some numbers that would represent like the importance for the different symptoms in coming up with this explanation, right? So in the example here, for example, the headaches and the sneezes would be like positively influencing the prediction, while no fatigue is actually like a negative prediction, right? And this could, for example, be used by a human to come up with a decision. And since these days there is like a big shortage of medical doctors, it is a good idea to try to automate this and give it to the machines as much as we can. Okay, so now how do we come up with explanations? I'm gonna tell you quickly about this famous way to do it, which is called LIME. LIME is short for Local Interpretable Model Agnostic Explanations. And basically what we are trying to do is, so let's say we have some problem, right? So we are trying to categorize, imagine you have some points in a 2D space, and you want to determine whether these points belong to the red cross class or to the blue circle class. And you run this through a machine learning model, and you come up with this funny looking boundary, right? So you have this thing that looks like an elephant in pink, and then so that's your model, but that's not good enough because that's really, really hard to understand. So you couldn't, for example, know what you do in a different way in order to change your outcome. So one way to fix this is if you look at any curve, I think, with a potent enough zoom, it will kind of look like a line, right? It is like as when we walk in the street, it looks flat, even though the Earth is round. So a similar notion is used here, right? So even though a model may be globally really hard to understand, locally it will kind of look like a line. So that is what we will do when we use Lime to come up with an explanation, right? So a visual way to understand how Lime works is the following. So let's say we have this image on the left, right? So it's clearly the image of a frog, but we want the model to be able to tell us that this is frog, and we want to be able to be sure that we know the reason why it guessed it was a frog are good enough. So the way the line model works is the following. So first, let's say we break down our image into what we call interpretable components. So basically, think of the image as a jigsaw puzzle, and then each of the pieces will be what we call an interpretable component. And then based on these interpretable components, we will create perturbed instances of the original image, right? So we will have different images where some parts of the image are actually hidden from the model and some others are shown to the model. So again, remember, we have some model that makes predictions, and we want to understand how the model is coming up with their predictions. So we do have access to these probabilities, right? So these probabilities, the probability of this being a frog, these are being generated by the model. So we are feeding it perturbed instances, and it is returning some probability of it being a frog. So based on this, we can, for example, feed a linear regression model based on the images and the perturbed images and the probabilities that we are getting. And then a linear regression model is basically just a linear combination of variables with coefficients, and the coefficients will tell us what the important features are, or in this case, what the important pieces of the image are. And that way we can come up with like an idea of which regions of an image are important in order to come up with the prediction that this belongs to a frog, right? And the nice thing about this is that you can actually run this through, like it doesn't need to be only for frogs, right? Like you can ask it, so what is the probability of this being like a pool table? And as you can see, this is actually not 0, it is 0.07. And you can even interrogate the model. Okay, but why do you think this may be a pool table? And it will show you like the parts of the picture that kind of resemble like pool balls or maybe the table or something like that. And likewise, so like a balloon, right? So this is kind of the idea on how you can explain a model, even though you don't understand the model at all. It is completely a black box model, but just based on the predictions that it is making, it is possible to come up with an explanation of what's going on. Okay, so now I'm gonna move into the thing that I'm more passionate about, which is fairness. So, okay, and I'm quickly gonna tell you a little story. I mean, there are loads of these stories, but this particular one has to do with Amazon, the company Amazon. So it turns out that they had this resume reading tool. So basically, whenever they offer a job, they will receive a lot of applications. They will receive thousands, if not hundreds of thousands of applications, and they need to sift through these applications in an automated way. So they developed this machine learning model that would discriminate some CVs so that they would be read by executives, and some of them would just be automatically discarded. And well, it turned out that this model, it was discriminating against women. So basically every single time a CV had the word woman or women in it, it would immediately be discarded. And this, of course, was like super shocking. It was a scandal, and Amazon actually had to take this model down, right? And yes, so basically this is what fairness is about. So fairness is about preventing this kind of discriminatory behaviors from classification systems or regression systems or any kind of automated decision-making systems. Okay, so in order to formally define what it means for a system to be fair, we need to come up with a few definitions. So the first definition that's important is the notion of a protected attribute. So we will say that the protected attribute of a data set are the features that are prone to a discriminatory decision, right? So there are a lot of different examples of what variables can be considered a PA, but like typical examples could be, for example, the ethnicity of a person or their skin color. It could also be their sex or gender. It could be their age. It could be their income, or it could even be their education level. So now we're going to be working on a simplified case. So we're going to be working under the assumption that the protected attribute is binary, right? So by this, we mean that we will only have two possible classes. We will have the favored group and the unfavored group, right? By class, we will mean the decision that the system is making, right? So for example, think of a university that's trying to decide whether they will admit a student into a particular program. So the outcomes of this, they can be either positive or negative, right? So it can be the case that a student gets accepted into the university, or it can be the case that the student gets rejected. So based on these things into the binary protected attribute and the binary class, we can split our data into four different population groups, right? So we can have the unfavored that got accepted, the unfavored that didn't get accepted, the favors that got accepted, and the favors that got rejected as well. Okay, so very quickly now. How do we define a system to be fair? So we can do it in many different ways. I'm going to just tell you two different ways in which you can define a system to be fair. So the first one is called demographic parity. So we will say that a system satisfies demographic parity if the probability of getting, so in this case, one is the positive outcome, right? So if the probability of getting a positive outcome from the system is the same regardless of your protected attribute value, right? So for example, if PA equals 0 are men and PA equals 1 are women, this would mean that the probability of getting hired by a company is the same regardless of your sex. So this notion of fairness is it has some pros. It's very easy to implement. It's very easy to check. You basically just take your data, split it by the protected attribute, and estimate like what the probability is of getting a positive outcome. So just basically count how many positives you're getting and divide that by the total amount of applications that you get. The cons for this, though, is that it sometimes doesn't really make a lot of sense to use. So an example here are similar arrest rates across sexes, or it could even be like some diseases are sex-specific, right? So there are some diseases that are more common in males than they are in females and vice versa. So therefore, demographic parity really doesn't make a lot of sense in many different contexts. A different definition that I think is slightly better is called equality of opportunity. And we will say that a predictor satisfies equality of opportunity if the probability of getting a positive outcome is the same regardless of the protected attribute, given that they do deserve to get a positive outcome, right? So in this case, we're not just talking about satisfying some quotas, but we are talking about people that deserve it. They are actually getting it at approximately the same rates for both protected attribute values, right? So This is nice because it actually prevents true positives mistreatment because of some quota system. But the problem with this is, of course, that this would not necessarily capture social inequalities, because it may be the case that one group is actually not being considered to deserve being admitted to a university, but this may be because maybe they didn't have access to the same quality of education as the other group. Okay. So those are the three definitions that are important for this talk, and just for you to understand what we mean when we talk about fairness. Okay, and then very quickly, I want to go through how a machine learning system usually works, right? So you usually start with a bunch of data. So you should probably think of this data as some sort of a Excel spreadsheet. So you have rows, which are instances. They are like different people. And then you have columns, which are like the different attributes or features in your data. So the way machine learning usually operates is that you take your data and you usually start by splitting it into what you will call the training data, which is what will be fed into the algorithm, and then some test data that will be used to test how good the final model is. And then based on this training data, we will select some machine learning algorithm, and the machine learning algorithm will try to find some pattern in the training data. And then based on these patterns that are found, a model will be generated. And then based on this model, the predictions will be made on the test data. And then we will know whether the model is good or bad. And ideally, we can deploy this model, and it will be used in over unseen data all the time. Okay, so there is a problem with this approach, right? So this is how machine learning works. But the problem with this is that this relies on having good quality data. And if your data is not good quality enough, the algorithm will come up with different problems. For example, here, I'm sure most of you will have used Google Translate at some point. I'm also sure that probably most of you don't speak Turkish, neither do I. But it turns out that Turkish is a gender-neutral language, right? So what this means is that the phrase "o bir doctor" could mean he is a doctor, but it could also mean she is a doctor. But the thing is, for many years, Google Translate, if you entered the phrase "o bir doctor," it would translate automatically this as he is a doctor and never as she is a doctor. They actually kind of fixed it. So if you try now, it will come up with this, right? So now it will say, she's a doctor or he's a doctor. And then everyone is very happy, and we feel like the problem has actually been solved. But the problem is it actually hasn't been solved, right? If you do this from English to any other language or any other language to English, then yes, it is solved. But if you try to do this from Turkish to Spanish, for example, it still doesn't work. It still defaults to he is a doctor, right? So they just partially fix it. And I don't know why they haven't implemented the same fix for every other language, because, I mean, if they can do it for English, they should be able to do it for every other one. Okay, the good news, unfairness can be detected, unfairness can be corrected. And if you're interested in this topic, there is a great resource that I recommend that's called AIF 360 by IBM, right? So they have a lot of interactive approaches there. So you can go there, use some data, test the different fairness definitions and whatnot, and you can have a lot of fun. Okay, so now, how can we correct unfairness? There are many different ways in which we can do this, right? So let's say we have some algorithm, and we know that this algorithm is not performing correctly. So it is discriminating against, let's say, I don't know, against a particular population group. There are three different ways in which we can try to fix this problem. So, and the approaches are usually referred to as pre-processing, in-processing, and post-processing. So by pre-processing, we mean we should modify the data from which the model will be learned. By in-processing, we mean to add some constraints or specifications to the algorithm itself, so that forces the algorithm to learn in a fair way. And by post-processing, we mean we let the algorithm, we don't care about the data, we don't care about the algorithm, and just after the algorithm has made its prediction, then we have some post-processing rule that will sometimes change the decision, right? So that's the approach that I like the least. And the one I like the most is actually pre-processing, is the one that I have done most. Okay, so I'm gonna now quickly tell you about 4 different projects I've worked in, and most of them have to do with fairness and a little bit of privacy and a little bit of diversity, but I'll save that till the end. So the first project I want to tell you about, it is about how a pre-processing pipeline for data can have an impact over the fairness of a machine learning system, right? So by pre-processing pipeline, we mean the set of steps that transform the raw data, so the data in its original form, into the data in the final form before being fed to the machine learning system. So usually when you have some data set, so again, imagine an Excel spreadsheet, you cannot just directly feed these into the system because most machine learning models, they will understand numbers. They do not understand text. They do not understand categories. And they particularly hate missing values, right? So if you have some cell in your Excel that has nothing in it, you need to figure out a way to fill out that missing value. So how to encode your categorical variables. So for example, again, if you have some category, a typical one would be like, for example, sex, which could be male, female. A very easy way to encode male, female is to make, for example, male 0 and female 1. And if you have more than 2 categories, there are different approaches with advantages and disadvantages, right? It's not as straightforward as 0, 1, because if you make it like 0, 1, 2, 3 or something, you are implying that there is some order in the categories, and this is not necessarily going to be the case. But there are solutions to that. Another thing that you need to do, as I told you earlier, is if you have some missing values, you need to figure out a way to fill them. Sometimes some approaches are really easy, but others are like more fancy. And optionally, after doing this, you may still want to do other kind of stuff, right? So class balancing refers to not having, for example, a lot of positives in your data and just a few negatives, or vice versa. Feature selection means like deciding which features you actually want the model to be looking at, and feature scaling refers to, for example, if you have an area in your data and you have an amount of money in your data, they will be in very different scales. And this usually is also problematic for the models. So you sometimes want all of your numbers to be in roughly the same scale. So the combination of all these things is what we will be calling a pre-processing pipeline. And it turns out that this has a very, very big impact over both the accuracy of a system, but also over the fairness of a system. So the plot I'm showing you here, I ran through like a lot of different pipelines, running like many different combinations of how to encode your data, how to impute it, how to scale it, and what's not. And this little cloud that you can see here are the different results I got for accuracy and for fairness. And as you can see here, they vary a lot. So in the bottom left corner, we have what we call the Pareto fronts for this set, which are like the optimal solutions in the sense that they are not dominated by any other solution. And that's what we want to be able to find, right? So basically, we want to know out of all possible combinations of pre-processing that you can do, which one would yield the best accuracy and fairness results. So how did we do this? We ran something that's called a genetic algorithm. So a genetic algorithm basically encodes each piece of data into one gene, and then you create populations, which basically mean like different pipelines. And then these pipelines are evaluated, and then based on how well they did, this borrows from biology. So basically what you do is that you give higher chance to reproduce to pipelines that perform better. And you also introduce the chance for mutations to happen in your sequences. And then based on this, you run this process iteratively over and over and over again. And things like this will happen, right? So depending on what your objective is, on whether you are more interested in fairness or whether you're more interested in accuracy, these trajectories show what happens when you run this genetic algorithm through many iterations. And as you can see here, this is quite nice because this approximates the optimal solutions very nicely. Okay. This is the effect of applying pre-processing to your data without actually trying to improve the fairness of the system, right? So this is just what unconsciously happens just because you're making some decision on how to pre-process your data. But it turns out that you can actually introduce fairness-aware or fairness-specific pre-processing steps, right? So one thing you can do, for example, is you can try to balance these four groups I was telling you about earlier, like the U plus, the U minus, the F plus, and the F minus. So usually the unfairness happens because the sizes of this data will be different for these different groups. So basically, you usually will have a lot of F pluses and a lot of U minuses, and not so many F minuses and not so many U pluses. And a solution for this is to try to make the sizes for all these four groups to be about the same. How can you do that? You can do that by either under or over sampling your data, or even do both things at the same time. Okay, I tried to make it a little bit combinatorial. So this is like my combinatorial proof of why this works. So first of all, let's say we have some data which only have two features. One of the features we are calling x, that's a continuous variable. So that could be, for example, the weight of the patient. And then we have some categorical variable, which could be the unfavored group and the favored group, right? So this could be, for example, sex, or this could be ethnicity. This could be any categorical feature that you can think of. So what we want to do, our task is to train a line, right? So we want to find a line that splits the negatives from the positives as well as possible. And if you think about it a little bit, this is the best line that you can come up with, right? So this line, everything to the left of it will be predicted to be a negative instance, and everything to the right will be predicted to be a positive instance. Of course, it will make mistakes, but mistakes are unavoidable. So how can we fix the fairness of this? So we can fix the fairness by either undersampling the negative instances in our data or oversampling our positive instances. And let me give you a quick glimpse about why this is the case, right? So for now, we will just look at the lower line. We will just look at the U line. We will ignore the favored line for now, right? So if we look at the U line, and we look at our optimal classifier, which was that line there. So everything to the left, again, remember, will be classified as a negative, and everything to the right will be classified as a positive. So what would happen then to this yellow square here? So this yellow square, since it's left of B, it will be classified as negative, right? But what happens now if we do some negative undersampling? So negative undersampling means to get rid of some negatives to the left of B, right? So if we get rid of these 2 points, what will happen is that B is no longer the optimal line, right? So we can actually now move B to the left because this line is better than the previous one, because now that blue circle that we have there, which is a positive, now it's correctly being classified instead of incorrectly being classified. So this is better. And what this will cause is that the yellow square will now be considered a positive instead of a negative. If we do negative undersampling on the other side, nothing happens, but that's not like really a big problem. Likewise, if we try to do positive oversampling instead of undersampling, that means probably using more copies of the positives to the left of B. Again, what will happen is that B is no longer the optimal classifier, but the optimal classifier is moving to the left. And again, the yellow square will be classified as positive. Oversampling to the right, again, has no effect over the optimal classifier. And we can do the same thing for F, but yeah, it is analogous, right? So it's exactly the same argument. And what we did in this work is that we tried to tune our algorithm to do the optimal amount of resampling. And we did this by introducing some resampling parameter. And this has the effect that it is expected to have. So I think it was a success. Very quickly, let me go through another. I have 2 more things I wanted to mention you. So second one is about privacy and fairness. Some of you probably already heard about this because I talked about this in dance last year. So I included this particularly because I wanted to mention privacy. So what is privacy? So privacy is wanting the system to not be aware of whether my data was used to train the system, right? So as a user, it is important for me to have the confidence that I am not identifiable in the training set of a model, because otherwise an adversary may make some inferences about myself if they get access to the training set. So okay, a few privacy definitions very quickly. We will call quasi-identifiers the features such that their values may be used to identify an individual. We will say that a data set is k-anonymous or satisfies k-anonymity if each record is indistinguishable from at least k-1 other ones. And we will call the indistinguishable records a k-group. And finally, we will say that a data set satisfies T-closeness if the PA distributions, remember PA is short for protected attribute. So for example, again, sex or gender. So if the PA distributions of every K group are similar to the distribution of the protected attribute for the whole data set, right? So basically what this means is if a data set has, like, let's say roughly 60% female, 40% male, we want every K group to preserve this proportion to be roughly 60% female, 40% male. Okay? So this is a visual explanation of how this works, which is probably much better. So in here we have some data set, some synthetic data that I generated for the example. And these gray circles that you can see here, they would all be K groups. Why are they K groups? Well, they are K groups because all of these points, well, actually, wait a second, they are not K groups. What these data sets are is that they are T-close. Why are they T-close? They are T-close because the proportions of blues to yellows in each of these circles is 2:1. And that's exactly the same proportion of blues to yellows in the whole data set. So these circles here, they are T-close, but not necessarily K-anonymous. So how can we make these K-anonymous? So we can make these groups K-anonymous by microaggregating them. By microaggregating them, basically what we mean is to take the averages for all of these groups and modify the original values for the average values. And in that case, in that way, all of the points become indistinguishable from every other point in the same K group. And now our data set satisfies K anonymity, right? So basically, we have sets of 3 points. So this would be 3 anonymous because we have groups of 3 dots that are indistinguishable from each other. Okay, so very quickly, how can we do this, right? So this is very quick. Fairness and privacy, they seem to be a different thing, but in a sense, they both relate to sensitive or protected attributes or protected data, right? So the thing is, they want to hide or conceal the protected attribute from something. Fairness wants to hide the protected attribute from a classifier, for example, while privacy wants to hide the protected attribute from some adversary that may make a misuse of our data. So in order to correct fairness in a private way, we decided to try to combine privacy and fairness at the same time. And the way to do this is the following. So we used an algorithm that's called the maximum distance to average, which does the microaggregation bit of K anonymity. So the way this algorithm works is as follows. You start with some random data, and then you find the average of all your data points. That's the yellow crossing here. And then you find the points that's furthest away from your average. So that would be the green rhombi on the bottom left. And then once you find that point, you take all the points that are closer to that point. And that will be your first cluster. So you will say that all of those points are the closest they can be. If we can have like groups of size, let's say 4, right? And then you repeat over the points that are still unassigned. So again, you find the average, You find the points that's furthest away from the average, and then you find the points that are closest to it, and that would be your second cluster. And then you repeat, and then you end up with having three clusters in this particular case, right? So those would be the points that we will aggregate in order to ensure K anonymity. So the fair version of this does something similar, but the only difference is that instead of limiting ourselves to just using K points, we introduce another condition, which is that every single cluster that gets formed, the proportion of unfavored elements to favored elements should be similar to the proportion in the whole data set. And then we do the microaggregation. And then once you do the microaggregation, doing fairness correction becomes trivial, because since all of these points are indistinguishable from each other, all you need to do is to change the labels of some U pluses, of U minus into U plus, or from F plus into F minus. And either way, you can fix the fairness in the problem, right? This is a quick example, but I feel like I don't have a lot of time left. I mean, I guess I very quickly could tell you, like, in here we have a sample data set to the left. So remember, we have some feature that's X and some protected attribute, that's PA. And then based on these, we will find the mini clusters that we are looking for. That's what we call the 1-2 fairlets. We call them 1-2 fairlets because we want every group to have one unfavored element and two favored elements, right? So that's why they are 1-2. And then once we find these fairlets, we combine the value for X. So basically, for example, for all the pink instances, instead of the X value being 1, 2, and 11, what we do is we take 1 plus 2 plus 11, and then we divide by 3. And that's why the XMA, MA is short for microaggregated, is 4.67. And likewise, for the blue points, we take 3 plus 12 plus 13, and we divide by 3, and then we end up with X microaggregated 9.33. And now the points are indistinguishable from each other. And then the second thing we do is that we modify the class. So the class was the original class, and we can just tweak the values for the for the favorites and the unfavorites, so that they satisfy any notion of fairness that we care about. Okay. And just to finish, I think I still have like maybe 5 or 10 minutes left. So I will very quickly use this. I know this is a combinatorics conference, so I just wanted to mention this because this is like something I've been working on recently. And this has to do, I mean, actually this originally, the first time I started thinking about fairness in graphs was with Julian, because we started talking about this in dance last time we met. And then I forgot about this like for a year. And then recently I started talking to a different colleague. And our idea was, how can we turn very commonly used graph algorithms into like something similar to a fair version of the algorithm, right? So, the first example we came up with is what we call diverse minimum spanning trees. So I'm pretty sure you're all very familiar with the Kruskal's algorithm, or Kruskal. I'm sorry if I'm mispronouncing it. So it will generate a minimum spanning tree, right? But the thing is, if, for example, your graph is edge colored, Kruskal probably, of course, will not care at all about the colors of your edges, right? So we decided to try to change this, and we introduced like a very slight modification to Kruskal's algorithm that has a tuning parameter again, which we call D for diversity. And this parameter goes from 0 to 1. And when D is 0, then you have Kruskal. And when D is 1, you have a very diverse, but not necessarily very efficient minimum spanning tree, right? So the way it works, it's basically the same as Kruskal. So this is the algorithm. The first two steps are the same, right? So basically, you take all of the vertices in a graph, but none of the edges. And then what you do is that you sort your edges. The difference with Kruskal is that in Kruskal, you just sort by the weights of the edges. In this case, we will sort by a convex combination of the weights of the edges. That's the first term in SE. And the second term is like how often a particular color occurs in the tree, not in the original graph, but in the tree. And then we basically, so this is like a scoring function. And then what we do is that we sort the edges by this scoring function. And then basically all we need to do is to check the cross-kernel condition, right? So basically for every edge, we check. If adding it does not form a cycle, then we add it to our tree, and otherwise we don't. And then when we find one, we break and we go back to compute the scores for the remaining edges. As you can see here, we run it over like some synthetic graphs using two different random graph mechanisms. One of them is called the Erdős-Rényi mechanism, which is basically a uniform probability of existence for every edge in a graph. So you fix the number of nodes, and the edges have certain probability of existing or not. And then Barabasi-Albert, it's not about having the same probability, but it is about the connectivity of nodes. So basically, every new node you add to the graph, this is a constructive method. You specify how many of the previously existing nodes it will be attached to, right? So we try this out over both families of random graphs. And as you can see here, we have this trade-off. So weight sum is on the y-axis, and entropy, which kind of measures diversity, is on the x-axis. And the colors in the plot, they represent the diversity parameters. And as you can see here, we have a trade-off, which is like the higher your diversity, of course, the lower your weight sum will be. And this is to be expected, but it is nice that you can control this through a tuning parameter G, right? So just in conclusion, this was like I hopefully short introduction on responsible AI. And we basically introduced three different notions of what it means for an AI system to be responsible, right? So we introduced transparency, which lets us understand what the system is doing. We introduced fairness, which detects and corrects potential mistreatment. And then we introduced privacy, which keeps data safe. And finally, we also mentioned that there are other possible values that can be looked into, such as diversity. And that's pretty much it. So thanks a lot for listening, and please let me know if you have any questions. I hope I didn't overrun.
Okay, thank you very much, Vladi, for your talk. I don't know if we have a question. Thank you.
Oh, let me stop sharing now. Sorry.
I don't know. Somebody have question, comment?
Yeah, I have one in the Cruzcal case. It was like in the you wanted to add edges from the other class, from the protected class, like the same some number of times.
Yeah. So you start with a colored graph, right? So the graph has like a colored edges. Originally, it was colored nodes, but we were only considering two different kinds of nodes, right? So we were only considering unfavored nodes and favored nodes. And this induces a tree coloration of the edges, right? So you have edges that go from favored to favored, unfavored to unfavored, or combined, right? Like U to F or F to U, right? So, and then we decided, okay, like we really don't care about the color of the nodes. So we decided to just look at the color of the edges so that we can generalize more. And yes, so basically you start with some graph that has some edge coloring. And then what you want to do is that from this graph, you want to generate the minimum spanning tree, but you want to try to make sure that the spanning tree is as diverse as possible. And we also actually consider two different choices, right? So one of them is to make the spanning tree diverse, which means try to make the number of edges as close as possible. Like try to have, like, for example, if you have three colors, try to have 1/3 blue, 1/3 red, and 1/3 green. And the other case that we have also solved is if you want to make them not necessarily diverse, but proportional to the original graph. So if the original graph has like 40, 40, 20, you want the spanning tree to also be 40-40-20. And this is also like very easy to achieve by just tweaking the scoring function of your edges.
Oh, that's cool.
More comment, question? I have a curiosity about how it works in the real life. If Amazon detect that they have a problem with the program because it's discriminatory, and then they have a special team that work of this, or only the people is working of this, and sometimes you contact you.
So yeah, actually, this is like interesting. So some teams that they used to have a team that would work on this. So, but Trump happened, and then everything's Trump and Elon Musk and all that. Like things are changing. So, for example, it used to be the case that Twitter, they had a diversity team and like a responsible AI team. But when Elon Musk arrived to Twitter, he decided that they were not really necessary, they were not really important, and he just fired everyone there. So I think like responsible AI is more limited to academia now, but it is still important at the very least to be able to detect that these problems occur. So maybe they will not want to change them at first, but if you detect them and like expose them to the public, they will be forced to do something about it.
Okay.
I think. I hope.
Yes. And it seems that like Amazon will be many things. I don't know, for many services. Yes.
Yes. No, that's right. And just to clarify, like this is not Amazon's fault completely. So the problem is not with Amazon. Like they decide, no, we don't want any women, so we will make our algorithm to discriminate against women. It's more the case that the problem is they learned a model from a very big collection of CVs, right? But the problem is historically the computing companies, they have hired more males than females. So the training data that they have, it shows that males should be hired more than women. And that's what the algorithm is learning, right? It's not like a person is making this decision. The problem is the data is biased because of societal problems. But they still should be like detected and corrected, obviously.
Okay, thank you.
Yeah.
So thanks again, and if there is not a more question, comment, we will continue. Now we will continue with our presentation in YouTube, poster and video talk, and tomorrow we have the last session in live to this CaRT 25. So thank you very much, everybody, and see you tomorrow 10 a.m. Mexico time. Bye-bye. Thank you.
Thank you. Bye-bye. See you tomorrow.
Bye.